Alrighty, hey Mr. Helt. So I'm presenting number 3 in problem set number 44. So let's just get right into this. Part A, explain why it's correct to use the DMM in parallel with the potential difference you want to measure. So the reason why you do it in parallel is because the V, the potential difference, remains the same across both of the arms in parallel. So there's the same V for both of these. If you did it in series, the potential difference sums in series, so it wouldn't be as good to measure. For part B, we are asked how much current flows through this particular circuit, which is illustrated right here. What's the potential difference you calculate based upon that current flow, and how is that different from the quote-unquote true potential difference? So these are kilo ohms, and this is mega ohms. So this is several orders of magnitude greater than the resistance in other areas. When you calculate the equivalent resistance, you have the 10 to the 3 ohms, 1 kilo ohm from here, and then you have these ohms, the 1 over the 1 over stuff from the resistors in parallel. When you calculate it out, what you'll see is that when you put a large resistor in parallel with a small resistor, the large resistor essentially has no net effect on the equivalent resistance for this particular set of resistors in parallel. If this was just 2 kilo ohms, this would be 2,000 ohms right here. But with this 10 mega ohms, it becomes 1,999.6 ohms. This should say 2,000 ohms, by the way, not 3,000 ohms. My apologies. So essentially, what happens is large resistor in parallel with a small resistor, the large resistor has no net effect. And what you can think of it is like if you again look at a situation like this is a large resistor, this is a small resistor. For example, all the current will just flow through the resistor that is smaller rather than the resistor that is larger. The large resistor essentially bottlenecks this area, so it is almost equivalent to just having a small resistor there. So what you'll see is that you get 2,999.6 ohms as the equivalent resistance for the entire circuit here. And this is ignoring sig figs, and I only ignore sig figs here because I just want to see what the precise small difference is at the end. Using V equals IR, you can get the current that comes out of the battery, right here, the current for the circuit, and the current through the DMM for this particular parallel arm is just using V equals IR again. You can just take the fraction of the current that goes through that resistor multiplied by I, and you'll get that, you'll get that the current through the DMM is 6 times 10 to the negative 7 amps, basically inconsequential. Again, knowing that this is the current, you multiply that by 10 times 10 to the 7 ohms of resistance, and you'll get a potential difference of 5.9996 volts, which makes sense because if this entire thing wasn't here, there would just be 6 volts of potential difference across this 2 kilo ohm resistor. The addition of this 10 mega ohm resistor means that the potential difference across this set of resistors in parallel is 5.9996 volts. So in conclusion, to answer the final part of B, the difference is so minuscule that I had to keep track of 6 times more sig figs than I was supposed to in order to track it. Essentially, the reason why you keep voltmeters in parallel is that not only do they really not affect the current or the equivalent resistance, they also have the same potential difference as the potential difference you're trying to measure. So this brings us on to part C. So in part C, we're finally on the same order of magnitude. And here we see that the fact of the resistor being in parallel, the fact of the resistor being on the same order of magnitude has an effect. So calculating the equivalent resistance for the entire circuit again, we get that it is 8/3 mega ohms. This is in contrast to the 3 mega ohms it would be without this 10 mega ohm resistor in parallel here, which would be 9/3. Using V equals IR, we can get that 9 equals I times 8/3 mega ohms, so I is 27/8 microamps. Yes, so the current through the DMM is 27/8 times 1/6. That 1/6 is 2 over 10 plus 2. Essentially, it is the proportion of the current that'll go through this resistor with greater resistance, and that's 9/16 microamps. But again, very tiny number. The potential difference without the DMM, this is 3 mega ohms of equivalent resistance. So the potential difference across the 2 mega ohm resistor in series with the 1 mega ohm resistor would be 6 volts. Makes quite a lot of sense. 2/3 times 9 is 6. And with the DMM here, it's 9/16 microamps times 10 mega ohms, and that is 5.625 volts. So there's about a 6.7% difference between both of these, which tells us that when they're on the same order of magnitude, when the DMM is on the same order of magnitude as the other resistors, then you start having an issue. So yeah, that is my summary of this problem. I hope you have a great day.